For this engagement check, we are going to be talking about fluid dynamics. And aside from all the work that we did earlier in the semester talking about gravitation and Kepler's laws, this is one of my favorite parts of this class. There's a lot of active research that goes on right now in fluid dynamics. Fluid dynamics covers all parts of our universe, things happening here on our Earth and in our atmosphere, in our blood, in liquids, in the ocean, in clouds of other bodies in our solar system, for instance, Jupiter and Saturn. It governs how we are able to fly planes. So this part of the class, I think you'll also find will be really applicable to just about any future career that you will have. So this is the intro slide that I have for these sections. I didn't talk about them yet, but here we have a sphere that is inside a fluid flow. Let's say it's water, and it's got some particles in there so we can trace how that fluid flows. Now, the fluid is going to flow around this object here, but so it's going to flow around the object on the top and the bottom. But on the back side of the object, it creates turbulence. It creates these little kind of swirling vortices, or what we call eddies back here, swirling eddies. And then you have some interesting shapes, patterns of the way that the fluid will flow behind the object. And this can impact things like the pressure difference between the front side and the back side of this object as it's moving through fluid. Here is fluid moving past an airfoil, like the wings on a plane. And you can see here, the fluid comes to this point and it separates. It goes around and above the foil, and it goes underneath the foil. And then you create these really beautiful vortices on the backside as well. This is fluid dynamics, fluids in motion. In the majority of the fluid dynamics problems we'll be working through here, we will consider an ideal fluid. An ideal fluid has a lot of properties. We're making a lot of assumptions about these fluids that are probably not necessarily true. An ideal fluid is non-viscous. That means there's no internal friction between adjacent layers in the fluid. The fluid is incompressible, so its density is constant. Even if you apply a pressure to it, you don't change its density. The fluid motion is steady. The velocity, density, and pressure at each point in the fluid is constant in time. It's not time varying. And when you start varying all these things in time, things get a lot more complicated. That was part of my PhD too. And we assume that these fluids move without turbulence, although we will see a little bit later some examples of fluids with turbulence. So each element of the fluid has zero angular velocity about its center. So if something is turbulent, imagine the fluid parcel is going to be spinning around or rotating around some center. So in this case, we're going to assume we've got essentially a laminar flow, which is what's happening here. The flow goes up and over the parts of the airplane without creating turbulence. Although inside here we do, so these lines here are tracing out what we call streamlines of the fluid along the direction of the fluid flow, okay? Kind of shows the vector of the fluid. And it's going nicely over this airplane. But down here, we've got fluid inside two pipes of varying diameters and shapes here. So we've got fluid coming in from this direction and fluid coming in from this direction, and where they combine together, they're creating a little bit of turbulence right here. Let's talk about flow rate. Flow rate for a fluid is the volume per unit time that passes through a given cross-section. So let's imagine we have a pipe. Here is our cross-section, okay? And so we're going to use Q here to represent our flow rate. So Q is our volume that passes through this cross-section right here per time, the volume of a fluid per unit time that passes through this cross-section, okay? Now we can write volume of this kind of cylindrical shape here as the cross section of the cylinder, so A, times the length D, some unit length we'll call D. So the volume of this pink cylinder is going to be cross-sectional area times this distance D, and we're dividing it by time. And guess what? Velocity is equal to a distance over time. So this distance over time is a velocity, so you can make this equation that we originally started with, the flow rate is equal to the volume per time, and we can say that this is also the same thing as the cross-sectional area through which that fluid is moving times the speed at which it is moving. So the flow rate, we can use two different expressions for it. Okay, so we've got that rewritten here. Q is equal to the volume over time. It's also equal to the area, cross-sectional area of a tube, let's say, times the speed. And our flow rate is always has units of length cubed per time. So in this case, usually we're going to use meters cubed per second. We also have something called the equation of continuity, which comes in part from our flow rate that we just saw. Okay, mass in our universe is always conserved. So because mass is conserved, and we're going to assume that we have a steady flow inside this tube that we have here, the mass that flows into this cross section here of this wider end of the tube A in some time delta t must equal the mass that flows out through the smaller cross-sectional area of the tube A in the same time delta t. Okay, so that's saying that the mass of my fluid that's moving through this cross-sectional area in some unit time needs to equal the same mass of the fluid that's moving through this cross-sectional area per unit time. The only way you can make that work is if in the smaller cross-sectional area, you're moving faster and you're moving through this larger cross-sectional area. So our mass continuity says the same amount of mass coming over here through this cross-sectional area of the tube has to equal the same amount of mass that's coming over here through this cross-sectional area of the tube. So the flow rate has to be the same through this cross-section and this cross-section. So we say that the flow rate through cross-sectional area 1 equals the flow rate through cross-sectional area 2. That is mass continuity. Whatever mass comes in has to be the mass that comes out, okay? And then we already saw that we can rewrite the flow rate as the cross-sectional area times the speed. So then we can use this equation where we say that the cross-sectional area times the speed has to equal to the cross-sectional area times the speed at some later part of the system. Maybe we're changing diameter of our tube or of our system, or we're changing the speed. If we're changing the speed, that means we also have to be changing the cross-sectional area through which this material is moving. And we're going to apply that later to solve some problems that deal with blood flowing in our heart. Today I have Baby Yoda to help me here with all of these problems, so hopefully they'll be a little bit more extra. For this problem, we're going to think about blood flow in the heart. The aorta is our principal blood vessel through which blood leaves the heart in order to circulate around our body. Here's my depiction of the aorta. Okay, we're going to calculate the average speed of the blood in the aorta. Average speed, question mark. If the flow rate, which we're going to call Q here, if the flow rate is 5 liters per minute, and we also know that the aorta has a radius of 10 millimeters. So let's go back to one of our equations for flow rate. We said that Q is equal to, the flow rate is equal to the cross-sectional area of that tube or pipe times the speed at which that fluid flows through this cross-section, okay? So we have our cross-sectional area of our aorta right here. We know its radius is 10 millimeters. So what's the area of a circle? The area of a circle is pi r squared. So we can replace this area with pi
r squared times v is equal to q, okay? So now we want to solve this equation for v. So v, our flow speed for the blood that we're looking for, is equal to our flow rate divided by pi r squared. Okay, so we see though that our flow rate is given in units of liters per minute. A liter is a volume. Our flow rate is going to be some volume that moves per time, okay? So 1 liter, this is something we should remember, 1 liter is equal to 10 to the minus 3 meters cubed, okay? So if we're going to convert this, we want to convert this from liters to meters cubed and from minutes to seconds. So we're going to have a meters cubed per second for our flow rate. So we have to take our 5 liters and multiply it by a conversion factor. We know that in 1 liter, there's 10 to the minus 3 meters cubed. And then we need to multiply that by, so that gets rid of our liters and liters here, okay? And then we need to multiply by another conversion factor to get our minutes into seconds. So we know that in 1 minute, there's 60 seconds, okay? So then my minute cancels with the minute. So when I take 5 times 10 to the minus 3 and divide it by 60, that will get me my flow rate in meters cubed per second, okay? That's going to be our standard unit for flow rate. So whenever I do that, I find that my flow rate is going to equal 8.33 times 10 to the minus 5 meters cubed per second. And I have to get my radius from millimeters into meters. So r is equal to 10 millimeters, okay? And 1 millimeter is 10 to the minus 3 meters. So this is the same thing as 10 times 10 to the minus 3 meters, because 1 millimeter is the same as 10 to the minus 3 meters. Okay, so then my speed of the blood through the aorta is going to equal 8.33 times 10 to the minus 5 meters cubed per second divided by pi times the radius of my aorta, which is equal to, this is an equal sign, not a multiplication sign, equals 10 times 10 to the minus 3 meters, that's the radius here, and I have to square it. That's the same thing as 10 millimeters. All right, and then I find that punching this into the calculator, my speed of blood flow through the aorta is 0.27 meters per second. Now for part B. Blood also flows through smaller blood vessels that we call capillaries. Now we're going to have the rate of blood flow in our aorta still of 5 liters per minute. So when the rate of blood flow in our aorta is this 5 liters per minute, the speed of blood in the capillaries, these smaller blood vessels, is equal to, I'm going to call it V sub C for flow of blood through, or speed of blood through the capillaries is equal to 0.33 millimeters per second. Given that the average diameter of a capillary, D of a capillary, is 8 micrometers, calculate the number of capillaries in the blood circulatory system, N equals question mark. Okay, so what's happening? We've got our aorta, the blood is leaving through the heart, through the aorta, it's moving through our body. Eventually, that blood has to split into a bunch of different blood vessels, a whole bunch of different capillaries. But we know that the flow rate of blood through the aorta has to equal the flow rate of all the blood through the capillaries, even though all that liquid has to divide into a bunch of different vessels. That's what I'm representing here. The flow rate through the aorta has to equal the flow rate through all of these blood vessels. So I'm going to say Q1, the flow rate through our aorta, has to equal Q2, the flow rate through all of the capillaries together, okay? So the flow rate through our aorta, we already know. But the flow rate through the sum of all of those capillaries, that's going to equal, well, we've got the area, cross-sectional area of those capillaries, times the speed of the blood through all of those capillaries, which we're assuming is this number right here. It's the same for all of them, times, well, how many of them are there? We're going to represent that by a letter N. All of this fluid moving through the aorta splits off into however many capillaries there are. So the sum total of all the cross-sectional area times the speed of the blood in all of those capillaries has to equal the flow rate through our aorta. So we've got our mass continuity equation, which is the flow rate through our aorta has to equal the flow rate through all those capillaries, which we rewrote like this. So in here is the total number of capillaries. So we're looking to find the number of capillaries in our blood system if we know this to be true. Well, the number of capillaries in our system is going to equal the flow rate of blood through the aorta divided by the cross-sectional area of an individual capillary times the speed of blood through an individual capillary, okay? And we already found in part A, well, we already know the flow rate of that blood through our aorta, 8.33 times 10 to the minus 5 meters cubed per second. So that's our number on top here, 8.33 times 10 to the minus 5 meters cubed per second. And then we're going to divide it by the area of each individual capillary, which is going to be pi times the radius of that capillary squared. So the radius of these capillaries, we're given the diameter of the capillary. So the radius of the capillary is going to be half the diameter, which will be 4 micrometers. 1 micrometer or 1 micrometer is 10 to the minus 6 meters. So this is 4 times 10 to the minus 6 meters. And so I have to put 4 times 10 to the minus 6 here for the radius, and I have to square it. And then I have to multiply that by the speed of the blood through each capillary. And we're given the speed in millimeters per second. Okay, 1 millimeter is 10 to the minus 3 meters. So this is the same, 0.33 millimeters per second is 0.33 times 10 to the minus 3 meters per second. Now you can do the conversion factor if you'd like to prove that to yourself. This is also the same as 3.3 times 10 to the minus 4 meters per second. Okay, so here for my speed, I'm going to put 3.3 times 10 to the minus 4 meters per second. And then I find that I take 8.33 times 10 to the minus 5 meters cubed per second. That's the flow rate. Remember, flow rate is the volume per time. That's the flow rate through the aorta. And I divide it by the cross-sectional area of an individual capillary, pi r squared, times the the speed at which that fluid is flowing through an individual capillary. And then I find that then, this is how we can calculate the number of capillaries there are in total. Those number of capillaries is 5 times 10 to the 9. Okay, 5 times 10 to the 9 capillaries within our bodies. This example works exactly the same way for pipes in your house. You have the main water pipe coming in from the sewer system. Okay, that's your aorta. And then all that water has to separate into all the individual pipes within your house. Those would be our capillaries here, okay? The flow rate of all that water coming in through that big pipe from the city water system has to equal the flow rate going through all the individual pipes in your house. So it's exactly the same process here that you would use to calculate a similar thing when we're thinking about pipes in a house, or the way in which fluid gets diverted when it's moving through a river, and then it gets separated off into a bunch of little streams. So you can apply this principle to a bunch of other physical systems.
So I also want to talk about another really important equation in fluid dynamics, and that's called Bernoulli's equation. So as the fluid moves through a pipe of varying cross-section and elevation, the pressure changes along the pipe. The pressure changes when you change height along the pipe. Maybe the pipe starts up here and it goes down. The pressure changes. But the pressure also changes whenever you change the cross-sectional area of your pipe. So maybe you have a big area over here and you have a smaller area over here. All of those things change the pressure inside the pipe as well. So Bernoulli's equation states that the sum of the pressure and what we call the kinetic energy per unit volume and the potential energy per unit volume has the same value at all points along a streamline. A streamline is the path that one fluid parcel is going to take within your system. So you choose one point within your system and another point within your system. And then you have to satisfy at both of those points Bernoulli's equation. And they're the sum of the pressure plus 1/2 rho v squared plus rho g h has to equal the sum of all those quantities at some other point in your system, assuming you're moving along the same streamline, okay? So, for example, let's see, well, where does this equation come from anyway? It comes from conservation of energy. So this term right here, we said it was the kinetic energy per unit volume. That's the second term here. Kinetic energy is 1/2 mv squared. If you take that equation and you divide it by volume, remember mass was in there. If you divide mass by volume, you get a density. So the kinetic energy per unit volume is 1/2 rho v squared. The potential energy per unit volume, or our normal potential energy, was mass times gravity times height. If you divide that by volume, you've got mass over volume, which is a density. And where does this P out here come from? Well, work is a force over a distance. Okay, force over a distance. If I divide that by a volume, I've got distance on top and I've got a volume on the bottom. We saw earlier we can write a volume as an area times a distance. And so the distances cancel on top and bottom, so you're left with a force over area, which is a pressure. And that's where this comes from. Okay, it all comes from conservation of energy. Here we have in this figure, we've got semi-truck moving this way, car also moving, both moving to the left. And all these black lines, that's the streamline of the fluid. A particle of fluid or a molecule of the fluid of the air is going to want to follow along this path, okay? And so out here, we have fluid parcels that are moving to the right with the speed of v. But all of that same mass of air is going to funnel down and make its way in between this little alley between the car and the truck. Okay, whenever it does that, that fluid material has to enter a smaller cross-section. What happens when you enter a smaller cross-section from our mass continuity equation? When you enter a smaller cross-section, your speed has to go up. So the speed increases right here. And what happens when your speed increases, your pressure actually decreases. Okay, how does that work? When your speed goes up, your pressure decreases. And remember that the sum of all of these quantities right here has to equal a constant. Okay, so as that fluid is moving between the car and the truck and narrowing down to a smaller cross-section, we know that the speed has to increase. So if all this stuff still has to equal a constant, a number that does not change, if v goes up here, v squared, and assuming that everything's happening on the same level above the ground, so this quantity here is unchanging. So if v squared goes up, that means that the pressure has to go down in order for the sum of everything here to equal a constant number that is unchanging. So that means whenever you have a faster flow of fluid, you actually have a decreased pressure in that fluid. So the decreased pressure inside and between these two vehicles, decreased pressure here but you still have the same amount of pressure on the external bits of the semi and the car here. That's going to want to push those two objects together whenever that wind is going to rush past them. So it's actually a little bit dangerous to drive a little bit too close to a semi in your car because of this way, of this principle. So I'm going to ask you to apply, before you forget, the equation for mass continuity and the equation for Bernoulli's principle in order to answer this question right here. So we've got a pipe that narrows to a smaller cross-section, speed V1 coming into the left, speed V2 exiting on the right, cross-sectional area A1 on the left, cross-sectional area A2 on the right. We've got little pressure gauges here that are monitoring the pressure on the left and on the right. So through which cross-sectional area is the velocity of the fluid the greatest? You're going to think about mass continuity. And then, which is greater, the pressure at P1 or the pressure at P2? You're going to use your answer to this first question over here and Bernoulli's equation in order to think about the second question.